Welcome to another video for Stat 420. In this video, we're going to be introducing multiple linear regression. So there's going to be a lot of similarity here in terms of what we've already seen. The difference here is that we're just adding one or more predictors additional to having one to start. So the reason we call it simple linear regression is because it's simple. It's just one variable being used to model another variable. So multiple just means that we have two or more predictors that we're allowing to be in a model. And so if you think about what modeling typically is in statistics, where most of the time it's going to be more realistic that we're going to have multiple predictors that we're using to predict a particular response. So the question then just becomes, which predictor should I use? How much effect, or at least how much correlation, does each predictor seem to have? How much predictive power is it kind of adding to my model? Those are the questions that we're eventually going to look at. Again, we're still focusing on linear models here. So technically, we could add a quadratic term. We could add this relationship of this variable x2 and something besides a linear term. Besides just adding a constant coefficient. However, we're going to focus on just looking at linear relationships, and now in the context of having multiple predictors in our model. So this, by the way, is an example of a multiple regression model with two predictors. So notice that we have an x1 variable, we have an x2 variable, and the response is modeled by adding some value of x1 and x2, some coefficient that could be positive or negative. There's still going to be, again, an epsilon term to represent our model. Is probably not going to be perfect. That's why we're doing statistics, is we're trying to estimate, make a best guess based on our information. And again, an intercept term that just kind of anchors us to the y-intercept to just kind of have a reference point of where that model is going to be anchored. So I think a picture here is probably a good way to start before we get into some of the mathematics of what we're doing. So this is a picture offered in the book. So this is a way that we could visualize a multiple linear regression model with two predictors, where we have one kind of here on this first axis, one down here on the second axis, and then the response represented here on this third axis. So what we're doing is we have kind of a position based on these two predictors. So if we have these two variables, one of them is weight of a car, and one of them is the year that the car was made, and we're trying to use those two values to predict the miles per gallon of that car. So if we know what year it was made and we know what weight the car is, does that help us better estimate how many miles per gallon that car is going to have? And so we kind of notice a relationship here, right? So cars that seem to be in this sector over here tend to have lower miles per gallon. Cars that are more in this sector over here tend to have higher miles per gallon. So we're kind of seeing that relationship here, that miles per gallon goes up as year goes up, it goes up as weight goes down. And when I know both of those things, right? So when at kind of the intersection of those two things, I see a very strong relationship. Now, I will kind of mention here, we can make that visualization if we have two predictors, but as we add more predictors, technically we're adding more dimensions to this model, and it becomes very difficult, if not impossible, to really visualize what's going on. Actually, I'm going to go back to that slide for another second here. But if I only have two variables, you can kind of think about it's not really a best fit line anymore. It's really a best fit plane when I have two predictors. So notice that I can now kind of represent my estimate for NG based on a point on this plane. So, and I have a plane because I have two predictors now. But if I had three or more predictors, then it would be the next kind of dimension up. And the idea of representing this in a visualization is now just not really going to work. But if you want to think about it just kind of that way, is every predictor we add is kind of another dimension to my best fit geometry, or whatever is going to be there. So to find the least squares estimate when we have another parameter that we're trying to estimate, it just means that we're going to have another equation here. The process is still exactly the same, and the focus of this course isn't so much on doing this mathematical deriving. It's not It's meant to be a mathematically rigorous course. As much as we just want to know, like, this is not magic. There is reason behind what we're doing. So again, our strategy here would be to treat this equation as a function of beta naught, beta 1, beta 2, and as many betas as I'm going to have, as many predictors as I'm going to have. And I want to minimize what's called the squared residual. So the difference between the actual y values and my fitted y value, so kind of like my y hats. This if I added it all up would be y hat for a particular value. And then I want to minimize the squared error that comes out of that. So I can do that by taking this equation, taking the derivative of each parameter one at a time, setting it equal to 0, and then finding an expression of the parameter of interest that's going to minimize, that's just going to make this equation work. So it just means we have to do it one more time if we have another parameter there. Now, this is a little bit more important. Not that the previous slide is not important at all, but this is a little bit more practical, I think, and that is interpreting coefficients from a multiple linear regression model. We'll be doing that a lot. So it's still a similar setup if we're talking about the we'll call them the slope, values, even though, now that we have multiple multiple predictors, slope is kind of a fuzzier term to use now. But just this idea of, for every 1 unit increase in this predictor, we expect the response to be this many units higher or lower on average, right? So that part is still kind of relatively constant. The difference is that if we have other predictors in the model, then we kind of have to add this whole while other predictors hold constant to these interpretations of our coefficients. And that's because the coefficient for each predictor is only representing what happens if that predictor changes, but everything else in the equation isn't moving, right? So assuming that I have 2 cars of the same year, the coefficient on weight is telling me how much weight should affect the response, assuming year is just kind of staying the same, 2 cars of the same year, we might say. And then vice versa again. So if I'm looking at the coefficient for year, it's telling me something about how each year's impact or correlation with miles per gallon while looking at 2 cars of the same weight. So I'm going to kind of practice here by writing out this interpretation. So notice that we have a coefficient for weight. We have a coefficient for year. So I'm going to start with weight. For every 1 unit increase, I like to say unit because I can just use that word in any context, and maybe if I want to be really precise, I'll say like for every 1 pound or 1 kilogram or whatever it is, but since I'm not sure at the moment, I'm just going to say unit. For every 1 unit increase in weight of the car, we expect the MPG to, it looks like, decrease, since it has a negative coefficient, by 0.0066349 units, while year holds constant. Or you could also say when comparing 2 vehicles of the same year, if you want to, that's kind of a wordier version there. I usually just say while the other predictors hold constant. Okay. One other thing that I'll mention is that if you were to fit a simple linear regression model with weight and then do the same thing for car, you'd probably notice that the slope is often, it almost always will be a different value. And very often, not always, but often the slope will get a little bit weaker, like it will get a little closer to 0. Though I say that with a little bit of a warning that will not always happen, but often it happens. And that's has to do with the fact that if I'm looking at the effective weight when holding year constant, then there might be a little bit of correlation between weight and year as it is, right? So it might just be that as year goes up, car weights tend to go down on average. And so if I have both of these predictors, then them kind of in the regression model with the other won't have as singular big an impact as it would as a solo predictor all by itself. So just kind of a heads up here. these values will change when you go from a solo model to a multiple model, often getting closer to 0, but not always. And so they might even change direction, which might sound really odd. But depending on the relationship it has with the other predictor or predictors in the model, that coefficient could change in ways that are unexpected based on having that also in the model, which we'll be able to explore a little bit more in the class at a later point. Now I won't interpret the other beta coefficient, or I should say the other slope coefficient here, because it's just going to be the same kind of the same template here, but I will say something about the intercept here. So the intercept, this is just going to be interpreted when weight and year of car are 0, our best estimate for MPG is negative 14.637, etc. Now, let's also kind of make the observation we've done before. Is this a meaningful value in and of itself? No. That's because there are no cars in the year 0 that I'm aware of, and at least I don't, at the very least, I'm sure the sample of cars we're looking at does not extend nearly that far back, such that this would be like a really terrible extrapolation if I was trying to do that anyway. So we interpret the intercept not necessarily because it holds meaning in and of itself, as much as it's just kind of a placeholder. Like I said before, it's kind of an anchor in the equation that shows us where it's going to cross the y-intercept, if you want to think of it that way, just kind of as a reference point to make this equation work. So yeah. Now, this is where some of the math gets a little bit weird, and we don't necessarily care about some of this as much as we just want to set up the logic of what we're doing. So when we're doing multiple regression, we can kind of think about this equation in matrix form. And to kind of set that up, I'm going to step back a second and represent a simple linear regression in kind of vector form for reference. So it's a simple linear regression. Again, we also have a vector of y's, right? So for as many observations as we have in our data, we have an observation of y's that's going to follow kind of beta naught. And so this is going to be beta naught, and I'll just do this as a matrix as well, beta naught, just repeated over and over again. So for each kind of y value, it's going to be represented as beta naught plus some vector of x values times beta 1. So I'll do x1, x2 to xn times beta 1 plus, again, a vector of epsilons. Okay, so this is simple linear regression. So we have beta naught plus x, whatever x value we're looking at times beta 1 plus the appropriate epsilon, the amount of error associated with that data point. So whenever I have 2 or more predictors, I need to expand out this representation. So I'm going to go over here, and now I'm going to do MLR for 2 predictors. Again, I'm going to have y1, y2 to yn. So I have a singular vector of response variables. Now I'm going to have a column of beta naught still. But now I have double the amount of x values. So I'm going to have x11 and the second predictor, x12. And then I'm going to have, 21, x22, xn1, xn2. So I'm going to have 2 columns of x values, one for each predictor. And this is going to be multiplied by beta 1 and beta 2. So each of the slope parameters for each of those values. So I'm going to multiply x1, let me kind of use my laser here, x1 times beta 1, x12 times beta 2, And then for the next observation, it's going to be x21 times beta 1, x22 times beta 2. So what's going on here is it's kind of the as needed representation of however many parameters I have. I'm going to have that many x values. And I just realized I have like some random slide notes that are up there. So in case you're like, what is going on? This is just for me when I was creating my slides, and I just forgot to take it out. So this is how I create slides, is I make a bunch of bullet points and think about what I want to put on there. All right, so yeah, you can just ignore that. Okay, so the least squares math and multiple regression. We're definitely going to do some hand waving here. If you take an upper level regression class or maybe go to grad school for statistics, you'd probably maybe do this derivation as a proof, as an exercise or something. We're just content to say that this is true. So if I'm doing a least squares estimate for beta hat, I can kind of represent it in the matrix form, and I can find the vector of beta hats, the vector of best estimate for my betas, as represented with this expression right here. So the transpose of x times x, take the inverse of that times x transpose times y. Again, you might be wondering, why is that true? And it just has to do with doing some math to get from this expression to this expression to simplifying that expression to here. So I mention this because there might be one or two points where it's nice to know this, and we're going to use this to say that this is an expression of our best estimate for all the betas, right? So for beta naught, beta 1, beta hat naught, beta hat 1, beta hat 2, and we can use this, but we're not going to worry about exactly how we get here from this. And then one other note is just that we have some updated estimates for the standard deviation and variance of our residuals. So one note I'll just make is that we're going to, in the denominator, instead of n minus 2, we're going to have n minus p, where p is going to represent the number of parameters that we're estimating. So if we have beta naught, a beta 1, a beta 2, and a beta 3, then that means p is going to equal 4. And so that's how I would get that number. And so the reason that we're subtracting that out in the denominator is because basically an error correction. So whenever we're estimating variance with a sample result, we're going to overestimate that because we're making some parameter estimates in the calculations. For every parameter we estimate, we update our denominator by an additional value. Basically, we're going to make our denominator just a little bit bigger every time we have a parameter estimate. So again, it just kind of has to do with unbiased statistics and what happens when we're estimating variance with parameter estimates. The meaning is not so much important as just knowing this is going to be our expression for the variance of the residuals. This is our expression for the standard deviation of the residuals when we're working with multiple linear regression.